All right, guys, welcome back to another wonderful adventure in our CCIE journey with the Eigrp. In this particular lesson, we are going to be discussing traffic engineering with Eigrp and also unequal cost load balancing. So that's our goal today, is to cover this topic right here. We're going to be utilizing this topology for the process, and this topology I put into the Google Drive for you guys, so you can load it from later on if you want to go back and run through the video and kind of play around with some of the settings. It's already all pre-configured, but we've got a couple of loopback interfaces connected to router 1 and router 5, and those loopback interfaces are going to allow us to basically test unequal cost routing. We can see we have essentially 3 different paths here that have completely different types of metrics, so we're going to play around with that. And we're also going to take a look at some of the traffic engineering concepts. It's kind of a review of our previous discussion on classic Eigrp. You know, we're going to talk about things like the feasibility condition, how do we modify Eigrp path selection in the process, what is delay, what is bandwidth, how do we choose one route from another, and so on. And then we're going to kind of finish up by talking about unequal cost load balancing as part of this process as well. So let's start by kind of identifying where we are right now with this exact topology, take a look at some of the values, and take a look at some of the calculations, and see, based on that, if we can kind of do a quick review of what we discussed in the previous lesson, which was our our classic configuration. All right, so we're going to take a look at that. This topology is already pre-configured. So let me go ahead and just do a quick look at the routing information on router 5. If I do a show IP protocols, you can see we're running Eigrp for autonomous system number 1. We are using the named mode or address family mode configuration. I'm pretty much going to kind of stick with that for most of the concepts, because I have a feeling that on the written exam and on the lab exam, you are going to be required to know quite a bit about address family mode configuration. So we could do this in classic mode, but the concepts, the math, and the concepts that exist in address family mode are the same. It's just the configuration is slightly different. So we're going to take a look at this in address family mode. So we're running address family mode configuration here. We can see we have the 6 different K values, which we talked about in our last lesson, the rib scaling factor we talked about in our last lesson, and we're doing the 64-bit wide metrics in this particular case. So if I do a show IP route Eigrp, I should see that loopback route that's coming from the other side of the network. So let's just go ahead and do a little bit of investigation and talk about, get a better understanding of how these metrics are being calculated based on our last discussion. Some of you may have missed that. I think a couple of you missed that last discussion, but we will be talking about, I did make a couple of modifications. Hold on one second. So let's take a look at our topology. We did run into the last lesson. Ken, you'll be able to see this, and I can't remember if Mike, I think you were on the last lesson as well, but we had issues with that loopback interface reporting the appropriate delay in picoseconds. So I did do something in this particular case. I did actually put in a delay value. So if I do a show IP Eigrp topology for 192.168.0.0/24, we should see, oh, come on, that it has the appropriate value for picoseconds. So let's grab our topology here, because this is a discussion about traffic engineering. Specifically, how do we handle path selection, which is a pretty straightforward concept in Eigrp, although Eigrp does provide the ability to do unequal cost load balancing. I'm going to talk a little bit about how that actually is probably not very practical from an application perspective. But also, Eigrp is one of the only protocols that provides us the ability to actually have a backup route, if you will, to take over in case a primary route fails. So we're going to take a look at that as part of this discussion here. So let me grab a snippet of this topology real quick. And let's just put some numbers on this diagram and kind of take a look at, get a better understanding of why a certain path would be chosen over a different path and so on. So if I go ahead and apply some of the values to this particular topology, let's just visually taking a look here, it's probably pretty obvious that router 5 is going to choose the bottom path to get to the loopback interface on the left side of the network, right? And then, of course, router 1 would conversely use that bottom path to get to the route that's on the right side of the network. And so as a bit of a review, and in addition to really understand this concept of route manipulation and traffic engineering with Eigrp, we need to kind of do a little bit of backstory from what we had discussed in the very first lesson that we had in this class, where we were talking about feasibility condition, feasible successor, and so on. So from router 5's perspective, the interfaces that we're going to be concerned with regard to reaching that loopback is this interface here, and of course the loopback interface. So let's go ahead and use that path to kind of fill in the gaps about the different terminology and whatnot that we're going to be utilizing throughout this discussion here. So from router 5's perspective, it's obviously comparing the path metrics for the top path, the middle path, and the bottom path. And then based on those egress interfaces, it's determining which path is going to be the best path. So let's start by getting the values that are necessary for Ethernet 1.1 on router 5, and then we'll go from there. So show interface Ethernet 1.1, pipe include BW. So these are going to be the values that are used for Ethernet 1.1. We'll go ahead and put that on our diagram here in that direction. All right. And we'll do the same thing. Whoops. What happened there? We'll do the same thing for, well, we can assume that router 4, because I haven't changed any of the default values, we can go ahead and assume that router 4 is basically using the same values on its Ethernet interface. So we'll put that value there. And then as I stated before on the loopback interface, I did change the delay, but I did not change the bandwidth. So let's go to router 1 and grab that information from router 1. All right. Show interface, loopback 0, pipe include bandwidth, and these are the values that are set. All right. Now I did modify the delay. It was normally it would be 5,000 microseconds, but I changed it to 500 microseconds. All right. For those that weren't here yesterday, we ran into a situation with a loopback. In fact, I think I still have the document here where the loopback has a delay of 5,000 microseconds, but that was getting calculated into a total delay of 1.25 million picoseconds, which is clearly not the right conversion. But it turns out if you statically set the delay on the loopback interface, it correctly calculates the metric weight in picoseconds. So we were kind of banging our head against the walls yesterday trying to figure out why our calculations weren't coming out correctly. There were a couple of reasons, but the primary reason was that the picoseconds were not being calculated correctly for that particular interface. All right. So in the interest of making sure that we have the appropriate values, we can also take a quick look here and do a show IP Eigrp topology for 192.168.0.0/24. On this side, it's 1.0/24. And we can see that it is actually calculating the delay in the appropriate amount. And I could even actually add that value to our topology diagram, because we're now going to calculate the metric that's going to be used for this particular interface. So let's do the same thing for the other two, for router 5 as well. show IP Eigrp topology. And in this case, we're going to be looking for specifically, where's my diagram? The 172.16.2.4 subnet. 172.16.2.4/30. And that's the appropriate value for that as well. So we've got good values now to work with. And this will be a little bit of review of what we talked about yesterday, plus some other reviews of what we talked about in our first lessons, in our very first lessons. So if you guys recall, the formula, in fact, let me go ahead and pull that up from our discussion yesterday. I saved this into the Google Drive for you guys, so you'll see it in there. It's called Eigrp wide, or WM for wide metrics. But if you look at the formula for the bandwidth calculation, we take our reference bandwidth, which is 10 to the power of 7, multiply it times our wide scale, which is 65,536, divided by the worst interface bandwidth along the path in kilobits per second. So if I come back in here, I'm going to go ahead and look at the worst bandwidth. We can see the worst bandwidth is 10,000 kilobits per second. So the bandwidth is essentially going to be equal to 10 to the power of 7, right, times 65,536 divided by 10,000. All right, so we'll take that number and we'll put that into this value here. Now, if we were using K2, that would change. If you want to go back and review that other diagram or that other lesson that we did yesterday, we can identify how that would actually change. And then we've got these values here. The delay was essentially the sum of the delay. If I come back here, the delay in picoseconds, it's the actual sum. I should really change it. Sum of delays in picoseconds times our wide metric value, 65,536, divided by the Eigrp delay reference, which is what we call the Eigrp delay pico reference, which is 1,000,000. All right. So if we go take a look at our topology again here, we've got 5, 1, 2, 3, 4, 5, 6, 7, 8. Right? I think that's 8. 1, 2, 3, 4, 5, 6, 7, 8. Yep. And we're going to add, so that's 500 million. And then we're going to add 2, 1, 2, 3, 4, 5, 6, 7, 8. I believe it's 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. So that becomes our delay value. We multiply that times 65,536, and then we divide that by 10 to the power of 6. So that becomes our delay value for that calculation. Now I should be able to add those numbers together. Plus 65536,000, and that becomes our overall path metric. Let's make sure that I did that correctly. Show IP Eigrp topology 192.168.1.0/24, and I did not. So let's make sure I added up the numbers correctly. We also want to make sure that the numbers are being received correctly as well. So we see that in this particular case, we actually have in our topology database 2 entries here. So we'll go back and do the calculations, but it looks like my picosecond calculation was correct, unless I missed a 0. And the overall bandwidth calculation was correct for that particular path. Oh, that's the right number. Yeah, 229.37.6000. I was looking at the number down here. So we'll talk about why we see 2 entries here in a second. That's the whole point of this discussion. But you can see our number is actually correct this time, 229.376,000. So if I do a show IP route, Eigrp, you will notice for that particular destination, that's not the number listed here. We talked about this in the last lesson as well. This has to do specifically with the fact that we only have a 32-bit field in this routing table, in the routing information base, to store the metric. And oftentimes, because we're using a composite wide metric for Eigrp, it's a 64-bit field, so it could potentially exceed whatever we could store in our routing information. So you can actually see here from our topology output that the feasible distance was what we calculated. The routing information base metric is 179,2000. And that's because we're taking this number here and we're dividing it by 128. So if I divide that by 128, I get the 1792000, and that's just a way for us to scale that more granular wide metric down to a much more a metric that would fit actually in the routing table. All right, so makes sense. We're using the bottom path. We've got a metric of essentially 22, or whatever this number is, 2.2 million or whatever number is, for that particular path. So let's go ahead and put that on here. That is the metric for this particular path. Now, in fact, let's go ahead and put that in here. Metric equals, and let's just grab it from our calculator and multiply this times 128. There we go. All right. So that's the metric for that path. Now, that is still referred to as the feasible distance. Remember, the feasible distance is the shortest, or the overall path metric to reach a particular destination. What you're seeing in the second number in the database here, though, if I do a show IP Eigrp topology, is you're seeing for that particular destination, the 1.0 destination, this number right here is extremely important, and that's what we're going to be talking about today, which is what we call the reported distance, or sometimes it's referred to as advertised distance, not to be confused with administrative distance. So this is the reported distance for a particular path. And if you recall from our discussions in our first lesson, the reported distance is the cost for my neighbor to reach that particular destination. So this is the distance that's being reported to this router, which is a very, very important number. Now, as far as calculating the reported distance, it's very simple. The reported distance to router 5 is equal to the feasible distance for router 4 to get to that destination. So we don't have to do the math. We can assume that the math is going to work the same way. We don't have a problem with that in this particular case. So we're just going to document that on the slide here, because that's going to be a number that's very important for us to recognize with regard to Eigrp, specifically when it comes to the concept of traffic engineering and being able to identify not only the best path but the next best path. So we'll just grab that number from here. It's already highlighted, so I should just be able to put that into the document here. So the reported distance from this particular device is equal to that value there. All right, now you take that reported distance, and I'll just put it right here. You take that reported distance and you add the cost of this particular link here. That's going to get your overall feasible distance. So if I were to look at the alternate paths, if I was to look at the second path and the third path in this particular case, then, oh, and by the way, I forgot to mention that this becomes what we define as the successor route, right? Because it is the best path, if that makes sense. All right, so that is the successor route. That's the best path. So what Eigrp does, which is kind of unique, is not only does it pick the best path, but it picks the next best path. And again, that's something that we talked about previously, but let's see if that's in fact something that's happening here. Actually, we're seeing the path here, which is interesting, and this is where traffic engineering comes into play. I can see that I have one successor, But if I do a show IP Eigrp topology all dash links, I can actually see that I have two different paths to reach that destination. And that's actually kind of interesting. That tells me something about, well, it tells me two things about this particular topology. Number one, it tells me that there is the potential that I'm actually missing a path because I should have three paths. So there might be a misconfiguration that's preventing the third path from being from showing up. But it also tells me something about this other path through 3.5, through the serial 2.0 interface. So we're talking about this interface right here. All right. Now what's interesting is that the serial 2.0 interface is showing up, but this other path going up to router 2 is not showing up. So that actually lends itself, to me, it tells me that there's actually a misconfiguration. So before we actually go in and play around with some of these other values, let me do a show IP Eigrp interface real quick. So we are running Eigrp on all three paths. That's interesting. We do have a peering relationship as well on all three interfaces. So that's kind of an interesting concept. I should be learning about that route, the 192.168.1.0 route, through all three paths, but I'm not learning it through, let's go back to our topology diagram. I'm not learning it through the Ethernet 1.0 path. I'm learning it through the 2.0 and I'm learning it through the 1.1, but I'm not learning it through Ethernet 1.0. So I do have a peering relationship between R5 and R2. That means that there's probably some sort of issue between R1 and R2. So let's go ahead and check R1 real quick. Show IP Eigrp interface. So I am running Eigrp. Well, that's really strange. I am running it on Ethernet 1.1 and serial 2.0 and serial 2.1. I have peers in each case. Let me do a quick show IP Eigrp topology. So the loopback is connected here. Let's go to router 2 real quick. Show IP route. And I am seeing the 1.0 subnet, and it is going out of Ethernet 1.0. Actually, this is exactly what possibly, well, I don't know if this should be happening or not. So actually it makes perfect sense. Okay, so router 2, and this is where we talk about the traffic engineering concept. Router 2 in this particular case has decided to go through router 5 to get over to router 1 because this serial link is going to have is going to be a less preferred path. The overall path metric to go to router 1 is going to be less preferred than if we were to go over back to R5 and then down to R4 and R1. So what's interesting about this concept is that well, it is going to make our lab here a little bit challenging. I might have to make a configuration change to make this work, but this could be a little bit challenging in that I won't be able to use that path as another path to get to the loopback interface. I could trick the router, I suppose, into thinking that that's an alternate path. Now, certainly if Ethernet 1.1 on router 5 were to go down, then this path would be a choosable path. Let me go in R5 and do that real quick. Interface Ethernet 1.1 and shut that down. Now, if I do a show IP route Eigrp, I can see that I'm going out of Ethernet 1.0 to reach that destination. And if I look at my topology diagram, so now I'm routing over to router 2 and then down to router 1. I'm trying to think if that's something that's okay for this particular exercise or if it's something that I want to change. Based on, sorry about the dog, guys. If that's something that I want to change based, sorry about that. if that's something that I want to change based on what our overall objective is here, and I think I actually will want to go ahead and make that change. Because I think that for the purposes of what we're trying to learn today, we really need to have 3 alternate paths that we can deal with here. So let me just make a quick change real quick. I'm going to delete this link in our topology here. And I'm just going to change this to a serial link. So bear with me 1 second here. Let's go with serial 2.3 on both sides. And this will be serial 2.3. And this will be serial 2.3. Now in this case though, I don't want to make this path look the same as the path through the middle here. We can initially, but we'll change it a little bit later on. So let's go back to router 2 real quick. Show IP interface brief, include up. All right, so config T, actually, let's just do a show IP interface brief because I'm going to have to take that other address off the Ethernet. Do show IP interface brief. So interface Ethernet, serial. Well, it was an Ethernet, wasn't it? I believe it was. That's strange. Go back to my topology diagram. So it was Ethernet 1.0. We're gonna change that to serial 2.3. Okay. So interface Ethernet 1.0, no IP address. Interface serial 2.3, IP address, and we'll just go ahead and assign this address to that interface. No shut. All right, and we'll do the same thing on router 5. Show IP interface brief, config T. That was why it was throwing me off because it was saying up, but there's actually nothing physically plugged into the port. But that's a GNS3 thing. Ethernet ports are always up for some reason in GNS3. That's why I was like, is there a cable still plugged into that port? Doesn't make any sense to me. But all right, so no IP address on that guy. Interface serial 2.3, IP address, and we'll just use this address here, 255.255.255.252. No shuts. All right. So that means now that we should have we should get an adjacency on that link, and I should also be able to ping 172.16 1.5. There's our adjacency. All right. So now if I do a show IP route, well, we're still using the same route for that destination. Actually, we're load balancing now because I had shut down that Ethernet interface. So let me go ahead and turn that interface back on. That was Ethernet 1.1. Config T, interface Ethernet 1.1. No shut. All right. Show IP route. Eigrp. All right. Takes a little bit for the convergence, but now we're going back over Ethernet 1.1. So, back to where we were. Let me grab, since our topology changed a little bit, let me just see if I can do this. It should work. If I just grab this part of the topology, I should be able to just paste that in. And I should be able to put that, overlay that. Get it exactly right. There we go. All right. So that's what our topology looks like now. It's not, this cable's a little bit messed up, but that's okay. That's going to bother me, so let me do it again. All right. Close enough. All right. So that's what our topology looks like now. The bottom calculations didn't change at all. We're still talking about the top two calculations. So we're back to the question of, do I have a feasible successor in this particular topology? We haven't modified any bandwidths or delays on these serial interfaces, so we know that those interfaces are going to have an equal cost metric. So if I do a show IP Eigrp topology, we can see that in this particular case, again, we don't have a feasible successor. Now, if I do all dash links, I can see all three paths are available to reach that 192.168.1.0 subnet. Now, in order to be able to classify whether or not a backup path or a secondary path meets the feasibility condition, what we have to do is we have to be able to verify that this number here, which is the reported distance for that backup path, is less than the feasible distance of the primary path. Remember, the metric is what is used, the overall path metric, which is the feasible distance, is what's going to be used to choose the best path to a destination. And that becomes the that becomes the successor. Feasible distance, which is essentially the metric, is how we measure the distance to that particular path. And we can see here that clearly this path has a lower overall feasible distance than these two paths here. Okay? Reported distance, again, is what's being reported by the neighbor to router 5. And from the topology table here, I can see that the reported distance for the serial paths, the serial links here, is 1767943958. So let me go ahead and copy that value real quick. And we're going to put that in here as RD. And I'm just going to do it for this middle one here because we're going to end up modifying the top one in a little bit. So that is the reported distance from router 3 to router 5 for that particular path. That means that this path does not meet the feasibility condition because 1767943958 is higher than 2293.76000. So what's going to end up happening in this case? Let me see if I can demonstrate this concept. If I do a ping, persistent ping from router 5, and I source that ping from, let's do 192.168.1.0 or 1.1, and we'll source that from 192.168.0.1, and we're going to repeat that, I don't know, 100,000 times. So I'm doing my pings here. Oops, let me do this. I got to do something different here. Hold on one second. All right. So I actually have to telnet to that router. Let's go through serial 2.3 because we're going to shut down Ethernet 1.1. So 172.16.1.5. All right. Oh, I need to set up privilege mode password too. All right. .5, sorry. I just set the password. Show IP interface brief. 2.6, sorry about that. All right. Try that again. All right. So now I'm in router 5. Let me go ahead and start the ping again. And now I can go in and I can shut down interface Ethernet 1.1. So what I'm doing here is I'm actually shutting down this interface right here so that what should happen is we should switch over to these routes here, but it's definitely not going to be a hitless switchover. All right. In fact, it's going to, you know, we're probably going to lose several pings in this particular case. So we can see that we missed, well, still timing out, timing out, timing out. So you can see that the changeover process is relatively slow from the perspective of routing, and that's for two reasons. It's for two reasons. It would actually be even worse if the path failed. In fact, let me go ahead and show you what I mean by that. So let's do a no shut. Come on. Why isn't it connecting now? Oh, because I was connected. I need to go to 1.6. I was actually connected to 2.6. So let me go back to 1.6 real quick. And do a no, config T. Interface Ethernet 1.1 no shut. So let me explain what's happening in this particular case. So first of all, the interface is going to come back up. Ethernet 1.1 is going to come back up. We're still doing our ping. We're still doing our adjacency. And you can see that we really didn't get any kind of hits when the interface came back up. The route was automatically installed and we started routing back over the primary path. But we saw quite a few hits. If you look at the loss here, we lost probably 6 or 7 pings in the process of the interface shutting down. This would actually be even worse if I went into this topology and I shut down Ethernet 1.1 on router 4. Because what would end up happening is that the neighbor relationship is still up between router 4 and router 5, so we're actually losing a route. Now we should get an update fairly quickly, but there are better ways to handle this process. All right, and in fact, there's another thing that I wanted to show you here. Because these two paths here do not qualify as a feasible successor, let me go into my GNS3 topology here. And what I'm going to do is I'm going to, we can probably just capture it on this link, show you what happens when I don't have a feasible successor. All right. What happens, let me explain it logically first, and then we'll go through the process of doing the capture. What happens is if I don't have a feasible successor and my primary route fails, so this path went down, I did know about these other paths. It was part of my topology database, but because they didn't qualify based on the feasibility condition, we have to send a query to those neighbors to identify whether or not those neighbors still have a route to that particular destination. Remind me later. In turn, those guys are going to have to query their neighbor to see if they still have a route to that destination, and then we're going to have to get replies for those queries back before we can actually start to utilize those particular paths. So we're adding essentially additional time that's required in order for router 5 to converge and identify that in fact that path is usable. So we've got our hello packets. We can filter out some of this stuff. Let me, because we don't really need the hello packets. We don't need the slarps. And we could probably filter out the hellos even. Let's leave those in there. So, because I remember I did this last time and Wireshark broke. I wasn't seeing any of the Eigrp stuff. So let's go ahead and go through the same process. We're going to shut down this interface here. And I'm doing a capture on this link here. So I should see, in this particular case, I should see that the query process taking place and the reply process coming back from each of the peer routers for that particular destination. All right, so let's go ahead and do that. Let's go into our router 5 and config T. Let's just do a quick show IP route just to make sure we're using the correct route in this particular case. And we are. We're going out of Ethernet 1.1. So I'm going to go into interface Ethernet 1.1, and I'm going to shut down that interface. Now what I should see in this particular case is a query, and then I should get a reply. And what this is indicating in this case is that the router has lost its connection. It lost its primary path to a particular destination. Actually, it's 3 paths in this case because we're also learning about these other networks over that same link. But this is the one we're focused on. It says, you know what? I've lost my path to this destination. Is there any way we can find, can you let me know if you still have a path to that particular destination? We can see the packet is being sent to 3.5, and if I look at my topology diagram, 3.5 is this interface right here. So the query is definitely being sent, and then I'm getting a reply from that response. I'm getting a reply from that query. So my question to you guys is, why does Eigrp do that, number one? And you guys can answer verbally if you'd like, or send a chat. Why is Eigrp doing this? Because it's slowing down the process of convergence. And then my follow-on question would be, how can I prevent Eigrp from doing something like this? Who wants to offer their opinion? Anybody?
I mean, it's because it doesn't have a successor, right?
Well, we have a successor. We were able to select our best. We did not have a feasible successor because, right, because the reported distance of that particular path was greater than the feasible distance of my successor path. That's why the query is taking place. But I'm talking about fundamentally, why does Eigrp even have this process? Why does Eigrp go through this process? We talked about this in our very first Eigrp lesson.
Loop prevention, dual.
It's a loop avoidance mechanism, and it has to do with the fact that Eigrp is a distance vector routing protocol. It doesn't have a complete picture of the topology. Because the reported distance is greater than the feasible distance of my successor, Eigrp says, well, that value might include the original path, which would in turn be a loop. So in order, we know it's not a loop because we can see from the physical topology it's not a loop, but Eigrp is not aware because Eigrp, well, quite frankly, is not very smart. It only knows about what it hears from its directly connected neighbors, and it doesn't know anything about any other information on the network. So that was the first part of my question. The second part of my question is, how can we engineer, which is what we're talking about in this lesson, how can we engineer it so that there is a feasible successor? Any thoughts?
Change the metric.
Change the metric, but specifically which interface, right? So if I'm looking at the metric for this path and the metric for this path, there's only a specific set of interfaces that I can modify that would allow me to make those paths qualify as feasible successors. In fact, there's only 2 interfaces that I'd be able to modify. I know I can't modify the loopback because that's going to affect all 3 routes, right? That will affect this route, and this route. I could do some sort of offsets or filtering, but we're not going to get into that right now. We could certainly do an offset. I could show you guys how to do that in this particular case. But I need to make it so that the reported distance for those paths is at least less than that value there. What we have to consider, guys, in this case is how is this value actually calculated? That's what we have to think about. How was that value actually calculated? It was calculated based on a bandwidth of 10,000, and it was calculated based on a delay of that value. Now, if we looked at the values, we're not concerned about this path here, and we're not concerned about that path here. because these paths have nothing to do with reported distance. These paths have everything to do with the overall feasible distance. We're not trying to make the feasible distance better. We're trying to make the reported distance better. So reported distance is what's coming from my peer about the same destination. And that's what we're focused on. We're focused on this link and this link. Does that make sense? So there's a couple ways that we could do this. We could apply some sort of offset on these routers for information that they're specifying, and that would be a quick way of doing it. I can demonstrate that really quickly. So let's say in this particular case, I'm on router 5 and I do a show IP Eigrp topology. Okay, so let me do an all dash. Oh, I got to turn the interface back on. All right, show IP Eigrp topology. We should get back over to the Ethernet. There we go. So this is our primary path. If I do an all dash links, I can see that I still have the 3 paths, but obviously these guys are not going to meet the qualification. So essentially I need to make sure that the metric in this case, the reported distance from my peers, is less than that particular value. So let's do that on router number 2. Config T. Now, this is probably not the recommended way of doing it. I'm going to show you that because this is something that they might have you do in the CCIE lab, where they say, make sure that this route takes this path, but then make sure these other routes take the other paths. You could certainly do that with policy-based routing, but you can also manipulate it with offset lists. So I'm going to do an IP access dash list extended, standard, excuse me, Eigrp offset for 192.168.1.0. And I'm going to say permit 192.168.1.0, 0.0.0.255. So I'm creating an access list that matches the route that I'm trying to manipulate. Okay? And then I'm going to go ahead and create, under the Eigrp process, router Eigrp CCIE. Now, in this case, the offset, we're on router 2. The offset is going to apply to the neighbor relationship on the interface. Now, we're running named configuration in this case. In classic configuration, you would just simply apply it under the routing process. But in this particular case, because we are a named configuration, we need to apply this under the address, under the AF interface option. I believe that's where it should be. Let's give it a shot here. So we're going to go under address family IPv4 unicast autonomous system number 1. And I believe it's going to be AF interface serial. You notice here we have all the interfaces available to us. We could do default if we wanted to. If I did default, though, the offset would apply to every interface. Well, in this case, I guess it's not a big deal because it would only apply to that interface and this interface. But let's make it clean. We're going to go serial 2.3 in this particular case. We're going to apply the offset to serial 2.3. Okay, so interface serial 2/3. Now let's see here if it's in here. BFD, passive interface, split horizon, summary address. That's interesting. I don't have offsets here. See, if I was doing this, let me walk through this process here. If I was doing this in, say, router Eigrp 100, I would just say, in this case, offset list. So I wonder if it's in the topology base. Offset list, and then I would specify the access list name, and then I'd specify the interface, and then, so I'll bet you it's going to be in topology base. So let's go back to router Eigrp CCIE, and let's go topology base. let's see, we have offset here, right, there it is. So it's going to apply to the topology. That makes sense actually, because what we're doing is we're modifying routes and metrics, right? And that's always done under the topology base. You can see administrative distance can be modified here, metric values can be modified, and so on. So in this case, we're going to go ahead and apply our offset list, and let's get the name. I shouldn't have given it such a long name, but let's see right here, Eigrp Offset. And then I'm going to specify out and the value that I want to offset. So if I go to router 5, this number here needs to be less than this number here. So if I take 176,794,3, oh shoot, 176,794,3,958, and I subtract 229,37,6,000, we have that value there. So I'm gonna set that value. That actually should not fix our problem, but I'm gonna set that value. And actually, it's probably gonna make it worse. Wonder if we should just do.
Hey, Scott.
Yes, sir.
When you subtract that number, that won't necessarily guarantee that you're less than your value. I mean, in general.
What do you mean?
When you just take the other number, and then just like divide it by 2 or something.
Well, that's the difference, right? But the question I have, let me see what that looks like in the topology table here. I believe it would actually add to that value instead of subtracting from that value. So that's not going to work for us. That would make the metric worse, right? You can see the reported distance went up, and of course the feasible distance goes up because the reported distance goes up. But if we're looking at our topology here, serial 2.3, so it did change it. It did modify it, and this is the number that we're trying to look at. But the number went up instead of down. So let's try it a different way. Okay, let's get rid of the offset. This is probably not the recommended way anyway. No offset. List. Why is it not? Oh, I see why it's not taking it. There we go. All right. That's probably not the preferred way of doing it anyway. There was another way I wanted to show you. I'll see if I can show you a little bit here. So we should see that reported distance should go back to its original value. Okay. And to answer your question, Tim, what we're trying to affect, it will affect the overall path metric as well. There's no doubt about that. But what we're trying to affect is we're trying to affect the administrative distance. Now, the reported distance, excuse me, not the administrative distance, the advertised distance, if you will, from the peer. So we could actually do that with a route map. We could set the metric. I already have the access list. So config T, route map, Eigrp offset, trying to think of how to do this. You know what? I'm going to come back to that. All right, I'm going to think about that in my head here because it's not a traditional way of doing it. It's really not the recommended way of doing it. The recommended way would be what Kamal said, which is to go ahead and change metric values. But I was trying to get a little creative and kind of give you guys an idea of how you could kind of manipulate individual routes and so on. So we will go back to that in a minute. Let me actually talk about the traditional way of ensuring that these paths are going to be feasible successors. Serial 2.1, serial 2.0, we need to modify these values on these interfaces for the egress for the metric for that particular, for router 5 to reach this destination. Now, if I consider the delays and the bandwidths that are being created or that are being used to calculate this path, I know that the worst bandwidth along the path should be less than 10,000 kilobits per second, right? Or should be better than 10,000 kilobits per second. Well, it needs to be less, but not, because if we made it better, then it might end up becoming, these might end up becoming the preferred path. Here's the point though. If I change the bandwidth on these interfaces to a higher value, it will not affect that portion of the metric because the worst bandwidth along the path is still considered to be these values. Now, is that a bad thing or is that a good thing? Well, we're not really trying to change the overall path selection. We're just simply trying to change the reported distance. That's a very, very important concept. We're trying to lower the reported distance of the paths so that they become feasible successors. So that being said, if I do modify the bandwidth of these interfaces, let's say we made them half of what's being reported for this overall path, right? Could we do it with just modifying the bandwidth, or could we do it with modifying the delay? We'd have to kind of play around with the numbers a little bit. We could certainly try modifying the delay first. That's always recommended because the delay is a cumulative value. It's a lot more predictable along the path than the bandwidth. So let's try and modify the delay of the serial 2.0 interface on router 1 to see if we can make that path qualify as a feasible successor. So let's go to router number 1. And if I do a show interface serial, which one was it? Serial 2.0. Pipe include bandwidth. So we've got a delay of 20,000 microseconds. Now on the Ethernet interfaces, we have a delay of 500 well, actually a delay of 1,000 microseconds on the Ethernet interfaces. So if I modify this delay to, to make it match, put it as 10,000 or 1,000 microseconds as well, would that make it qualify? Well, you have to do a little bit of math, right? But let's go ahead and just play around with it. So config T, interface serial 2.0, and we'll set the delay to 1,000 microseconds. Okay? Now, if I go back to router 5, I should see that reflected in the reported distance for that particular path. It might take a little bit for it to refresh, but the overall delay, actually, you know what? I modified the wrong side. I told you guys this 100 times. Only the egress interfaces matter in this case, and we're talking about router 5 getting to this loopback. Modifying this delay changes the metric in this path, but it has no bearing on the metric in this path. So I actually have to change it on serial 2.0 of router 3. Does that make sense? Only the egress interfaces matter when you're calculating metrics. R3 is calculating a metric to that destination. That's what's being reported to the router. So I have to use the egress interface. I have to modify the egress interface for that to take place. So that's going to be in router 3. Interface serial 2.0 in this case. And let's set the delay to 1,000 microseconds. I'll leave that there. So now we should definitely see a change in the reported distance for that particular path. And we can actually see that reflected here for 1.0. So the reported distance went down. We're talking about over the 3.4 subnet. So this is going to be 3.5. If I look at what's coming from 3.5, the number did go down significantly, right? 17679433958 is definitely larger than 522759958. Does it actually meet the feasibility condition? Actually, we kind of broke it, didn't we? This is where you have to be very careful when you're modifying these values, because it looks as though, no, it's not broken yet. It's still not the best path. The feasible successor is still, the successor is still the 229.37.6000. So it's still not the best path. It did change the overall path metric, but the question is that number lower than that number? Well, if I do a show IP Eigrp topology, I can see that it is not. Because remember, when I run show IP Eigrp topology, the only thing that shows up are successors and feasible successors. It's kind of unfortunate we're dealing with these really large numbers because it makes it difficult to kind of look at them side by side and see which one's smaller, which one's larger. But if we put it in Notepad, we should be able to see that. All right. This is the one that we modified. Yeah. So it's significantly larger still. All right. Now you could get on a piece of paper and you could start doing some calculations and trying to figure out what number is going to meet that particular condition. Or you can continue to play with different values. Let's try and change that delay to 100 microseconds and see what that looks like. All right, so now it looks like in this particular case, we still didn't modify the metric to the point where it's, let me make sure it's refreshed here. We still didn't modify the metric to the point where it becomes the preferred path. There's still our primary path, but we can see now the feasible distance of that, or the reported distance of that secondary path is that value. Where's my notepad? So it doesn't meet the feasibility condition yet, but it's definitely getting closer. All right. I know it seems like kind of like we're working with a sledgehammer here. But that's really, I mean, you could theoretically just calculate values if you put everything pen to paper and you start doing number calculations. But it doesn't really hurt to play around with this because you're not making that path more preferred, if you will. Now there could be a point to where you make these modifications where that could actually happen. But the concept is, well, it's pretty straightforward. So let's see if we modify it one more time. I mean, the lowest we can go is at 10 microseconds. Let's see if that gets us to where we need to be. All right. So now what's happened here is well, it doesn't look like it refreshed yet. Let me see. Yeah, it looks like it did refresh, but it didn't change by much. The metric is clearly going down, but we're still not in a position where this number is less than this number. So now we're kind of stuck in this particular case. And that actually is kind of interesting. Hold on one second, guys. So in this case, we're kind of stuck because of the issue that we have with, we can't change the delay to a low enough value to make that particular route a feasible successor. And we can always see that again by doing a show IP Eigrp topology, because what's going to be listed in this output is a successor and feasible successor. So now we need to kind of go, let me go back to router 3 and get rid of that delay. So now we're left with the other option is, we could certainly modify bandwidth, but the problem with modifying the bandwidth is that we have to make it better, and the only way to make it better is to change multiple links, right? We would have to modify this link here and this link here because bandwidth is always going to be based on the worst bandwidth. So now we're back to the scenario where we're doing our offset, all right? And we're offsetting the particular route. Now, what I was actually looking at was maybe a way that we could apply a route map to what we're advertising to the neighbor, and then using the route map to be able to set a metric that's going to be sent over to the peer. And I was just trying to figure out, because the problem with the offset, if we go back to our offset list, show run pipe section router, Oh, I took it out actually. If we go to our offsets, let me try something here. Config T, address family IPv4, topology base, and I want to see one thing real quick. No.
Hey, Scott,
Yes, sir.
couldn't you make a change to the actual successor for now?
Make a change to what?
Like do an offset on that?
You're breaking up a little bit. Could I make a change to what?
To the successor, so the existing feasible successor.
Well, you know, that's a great point, Tim. We could make the successor path worse so that it gets closer to the feasible successor path. And that's actually a great point. So we focused our attention on trying to make these paths better, but if I made this path worse, as long as I didn't make it so much worse that it becomes the less preferred path, I should still be able to close the gap between those individual numbers. I was just trying to think of a way that we could influence how the route is being advertised. Now, the offset would have worked, but the problem with offset is that we're not negating the value. But there was one way. I'm going to go back to what you mentioned there, Tim, in a little bit. Let me just.
That option? Sorry, what is the metric option, sir?
Metric is used for when you're actually setting the metric for. So if I say, let me see, metric. Yeah, maximum hop. So that's like the maximum diameter of an Eigrp domain, and then also default metric is for redistribution. But there was a way. All right, so I thought of something that we could do. We had created a access list. Show run access dash list. Show run pipe section access dash list. So we created this access list to match. Oh gosh, show access dash list. Did I not do it on this one? I must have. No, I'm sure I did it on it. Show run. I guess I didn't. Where did I create that access list? It must have been here. Show access dash list. Yeah, it is here. Okay, so we'll use router 2 as our to manipulate the value. So we're still on router 2 here, and again, the goal is to make whatever we're sending out to router 5 look better than so that it becomes a feasible successor. So I was thinking about this, and I thought, well, I could do an offset list, but an offset list will only allow us to add to the metric. It won't allow us to decrease from the metric. So what we could do is we could create a route map. So we'll just call it offset permit 10, and we can match IP address and match our access list here, and then we can set the metric in this case to the value that we wanted to set it at. Now, this is where I was kind of going down that other path of let's go ahead and subtract this number here from this number here to see the difference, and that's when we came up with this calculation right here. So I'm gonna do that right now. I know it's not going to work, but I'm going to do that right now just to demonstrate a concept here. So I can set the metric to that value, and then do a route map offset permit 20, and we're not going to do anything for that one. And now if I go into router Eigrp CCIE, now this is an offset list that's going to, a distribute list that's going to be applied to a peer. Let's see if it's under address family. IPv4 unicast autonomous system number 1, AF interface, and we're doing interface serial 23. And yeah, it's not there, so it must be under topology base. Topology base, distribute list. There we go. So we're going to reference our route map, and the route map is going to be offset. And we're going to specify that outbound, and we're going to apply that offset list to serial 2/3. And let's see what happens on router 5. So what should happen on router 5 is that this reported distance should go down to that value that we calculated here. This value here. It's not going to be enough, actually. That should be enough. Let's see. It didn't work. Yeah, it didn't work. Why didn't it work? Let's go back to router 2. Do show IP Eigrp topology for 1.0. We'll walk through the logic here again. Distribute list, route map, offset, out, serial 20. So if I do a show run.
Wait a minute.
Yes, sir.
For 220, which router is that? 220.
That should be what's going out of this interface here.
Okay.
So what should be
It looked like you were looking at router 5 and then that's serial 23. Okay, that's what you do.
Well, so here's my objective, right? I'm setting the metric for that route that's being sent to the neighbor on 2.3, which should be the reported distance that router 5 sees from that router now. Does that make sense? So the
what is your what does your prefix list say? Is it 172 or 192?
192.168.1.0/24. So let me pull up the whole configuration here. Route map, access dash list, and router. Okay. So here's the route map. Here's the access list. All right, we're matching the 192.168.1.0 subnet. Okay. Here is the distribute list out of serial 23 on router 2, saying that if you match route map offset, for some reason my route map didn't come in. Oh, because it's route dash map. So here's my route map. Match this address, Eigrp offset, set the metric to this value, which should be the reported distance then, because that's the metric that should be advertised for that route to that peer. Does that make sense? In fact, let's go ahead and change it to an easier number to read. Let's do route map offset permit 10. Match IP address Eigrp offset, set metric, and let's set the metric to, let's see, 1, 2, 3, 4, 5, 6, 7, 8. So 200 million, right? 200 million would definitely make it less. 2, 3, yeah, 200 million. Should have used classic because the dang numbers are so much easier to read. All right. So you guys follow the logic, right? I'm matching this route, 192.168.1.0, in the access list. And then the route map says, okay, based on that access list, let's go ahead and set the metric for that route. But I'm very curious if setting the metric is what's going to end up being advertised for that particular route. That's what I'm curious about. I've never done this way, but show IP Eigrp topology. So it's definitely not working because we can see it's not actually modifying what's being advertised. Let's see if it changes anything. Show IP Eigrp topology 192.168.
Hey Scott, this may sound like a stupid question.
Go ahead.
When you're putting the metric command in, is there any question marks after that or anything? What does that do?
No.
There's plenty of metrics.
Well, you know what? You might be right because maybe it's not a set metric. Maybe we have to set the metric values that are going into the calculation, right? So
Basically, the set metric is only for BGP, OSPF, and RIP.
There's the dang add and subtract. So metric value or bandwidth in kilobits per second. Yeah, it may not apply to Eigrp. I knew there was a plus or minus. That's where I found it there, was adding and subtracting. Let's just try something here. Show run section route map. Yeah, it may not apply to Eigrp. Yep. It's clearly not doing it. So let's go back to the easy way then, which is what Tim had suggested, is let's go back and, so Kamal says here, set metric, BGP, OSPF, RIP. Okay, so that would be...
I think it's only allowed for TCP, not Eigrp.
No Eigrp. Okay. Well, there you go. So you're not going to be able to do it that way. All right. So the only other way that we have is to make the other path appear to be better, right? Or worse, excuse me, so that it gets it closer to whatever this path is. So we can just modify the delay on this interface to a certain value, and we can kind of just pick random values here, as long as this still is the preferred path in the end. All right. So let's go into our, which one was that? Our 4 Ethernet 1.1. Interface Ethernet 1.1, and let's just set the delay. It's 1,000 microseconds right now. We want to make it a little bit closer to 20,000 microseconds. Let's just try 10,000 microseconds. And let's see how that looks on from this router's perspective now. Okay, so the metric definitely went up. No doubt about that. But it's still way, not even close to this reported distance from the other paths. So it might require a little bit of balancing from both sides, but I think you guys get the idea. Let's go ahead and change it to 10,000. No, let's make it 19,000. So I guess it doesn't really matter. We could even make it 20,000. Let's see here. So it's definitely going up. We're actually almost there, right? Let's see. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we're actually pretty close. All right. Let's make it 22,000. Almost there. Of course, you could calculate this on paper, guys, but I'm kind of doing it the lazy way. All right. So now it appears as though we're going to have our feasible successors. And sure enough, we do. All right. So obviously that's a much simpler approach. It's still the best path by far, but now we have a feasible successor. All right. So let's see, by having a feasible successor, how that affects our hit count on our switch over here. So telnet to 172. 16.1.6. And let's do our ping. That was probably way too far back. Ping 192.168.1.1. Source 192.168.0.1. Repeat 10,000. 168. And let's shut down our interface. All right. So the last time we lost about 4 or 5 or 6 pings. In this particular case, well, looks like we're losing about the same. So the convergence time didn't really go up. And that's interesting, because it should have gone up, right? Well, actually, in reality, because we have such a small topology, the fact that we're sending a query really doesn't change much the convergence time for Eigrp when a route goes down. But the only difference here is we wouldn't see the query in this particular case because we did have a feasible successor. So one of the things that I wanted to talk to you guys is obviously our goal here is to pre-calculate that alternate backup path in the network, so we get fast convergence when and we have this what we call fault isolation. The problem is the process is still in the control plane. It's still relatively slow. We see that we have our backup paths. In fact, if I do a show IP route, you'll see that I'm actually load balancing across those paths now for that particular destination right here. So it did assign those paths. I mean, it did insert those paths into the forwarding or the routing information base based on the fact that they were alternate paths. We did get rid of the query process, but the problem is that we did not. We still are relying on control plane functions rather than data plane functions for the failover. So one of the other things that I wanted to show you guys in this process from a traffic engineering standpoint, I think you guys understand the benefit of having the feasible successor, eliminating the need to do the query and get the replies, and we still would get faster convergence in that sense. But there's another feature that we can actually configure called bi-directional forwarding detection, which allows us to do test data plane reachability across our peers, as opposed to control plane reachability across our peers. And BFD is definitely something that you guys will have to know. We're going to learn about BFD for all of the different routing protocols, but it's a relatively simple thing to configure. You guys are probably using it at some point. It is a link level configuration. And so what I want to go ahead and do is I want to apply our BFD configurations to all 3 of these routers here and this router here for these links that are in between. And see if that allows us to achieve faster convergence. Now, I will kind of table this or put a little caveat on this discussion. If you're running BFD on a real platform, it's going to be a data plane function. Because we're running software routers, we're not running physical hardware, there's no ASICs that allow us to run this BFD function, we're not going to get a hitless transition. But the goal is to get it to the point where we have a hitless transition moving from a failed path to the backup path. All right. So let's go ahead and configure it between the two routers. I'm going to use some relatively aggressive timers in this case. Hopefully it won't crash the routers, but let's go ahead and do the configuration. So I'm going to start on router 5. And I'm actually going to use the address family configuration here is actually beneficial for us because I'm going to go into router Eigrp CCIE and go into address family IPv4, unicast autonomous system number 1. And this would be normally an AF interface configuration. So if I said serial 2/3, you can see that BFD is a configuration option that we have for the particular interface. All right, but because we have the default, we actually have the ability to set the BFD configuration on the AF default interface as opposed to the AF interface for a specific interface. Now, let me see if, yeah. So AF interface default, oops, I got to go back into the address family. AF interface default. And we should have the BFD option here as well. Now, it should give me the option to set the BFD parameters. And I wonder why it's not providing that option. Typically, this would be something that you would do under an interface. I might still have to actually do that on the interface physically. So let's see. Where's my topology diagram? So I might still have to go into these individual interfaces and set up the timers. I thought you could do that under the address family, but maybe not. So let's go into interface serial 2/3. And then we'll do 2/1, 2/3. And let's set our BFD interval. This is where you can specify, how quickly you want to send the keep alive messages. Typically, we'll keep this relatively low. It makes sense actually that this is an interface specific configuration because it is supposed to be done in hardware. So let's go ahead and set it to, 100 milliseconds. And let's say our minimum receive rate is also 100 milliseconds. And then we'll set a dead timer of 3. So a multiplier of 3, which is going to set our dead timer to 300 milliseconds. We'll do the same thing on interface. Uh-oh, I just crashed my router. I thought that would be too fast. Great. Hold on one second. I'm expecting some switches today, and I've got a sign for them. Damn it. All right, I got my switches. All right, I'm back, guys. Hey, All right. Hey, I need you to take care of something for me real quick, Gil.
Okay.
There's 2 switches that just arrived.
Yes.
Okay. Can you bring them in here and open them up, please? I want to check them before we have to send them to the customer.
Oh, these are the first term.
Yes.
It's replacement.
Yes. Sorry, guys. Give me 1 second.
We're going to need smart thing for these, right?
Yes, but I need you to open them up.
Oh,
Take all this crap off, open them up,
I got you.
put these power cords inside because we don't want to deliver them this way.
Okay, gotcha.
All right?
Okay,
They need to be at Storm by Tuesday morning.
all right. You have to configure it, right?
No.
Oh, just like you run them here and drop it out?
Yes.
Okay,
All right, guys, I'm back. Sorry about that.
let me know.
On Tuesday,
Okay.
which is kind of on the way, but I'm not going down until later. You could see how much it is to ship them. It might be kind of expensive, or you could drive them down. It's up to you.
I'll drive them down.
Okay.
Let's save you some money here. Yeah, because I'm sure if I go right now to ship them, it could be there Tuesday, but better.
Sorry about that, guys. All right. So, actually, Gil, we'll talk about that because all right. So let's go ahead and see if we can enable this again real quick. Router. We're gonna try one more time, but I don't know. I'm not holding my breath here. Let's see, router, Eigrp, CCIE, address family IPv4, AF interface default, BFD. I know we'll get the errors. Show BFD neighbor. So it's definitely, the protocol is definitely running. Let me do, yeah, see, it's already crashed again. So it's definitely, it's crashing the router here, unfortunately. I'm curious why it didn't crash on the other routers, but it did crash on this router. But anyway, what we're seeing here is a BFD neighbor, 172.16.1.5, and it's sending out these keep alive messages every, 350 milliseconds or 200 milliseconds. And if I was to be able to do, the command I would actually run is show BFD neighbor detail. Let me see if it'll run here. Yeah, see, router 2 has now crashed as well. So moral of the story, don't run BFD in GNS3 because it doesn't work. All right, but if I was to run a show BFD neighbor detail, you would see that the BFD process is tied to Eigrp in this case because it was configured under the interface for Eigrp. If we were to lose these keep alives or these messages between the neighbors, it's going to report back to the Eigrp process. We're not going to wait for an Eigrp hold time to expire. We're not going to wait for the control plane transition that Eigrp would go through. We would actually get a hitless reconvergence in this case because BFD would report immediately within that whatever timer you set for the maximum time. In our case, it was 3 times whatever our hello time it was. I think we set 350 milliseconds, so we're looking at about a second, I guess. In that case, it wouldn't be hitless. But in this case, we no longer care about reconvergence based on Eigrp hello times and hold times. And the failover time with no feasible successor, we demonstrated that. That was about 4 to 5 seconds. We lost about maybe 5 or 6 pings. If we were to be able to do this again with Bfd enabled, we would actually see that we might lose 1 ping only because it's software, not hardware. But in a hardware environment, it would be a hitless transition. All right. Unfortunately, I can't show that because, well, it just crashed. And I don't think I can recover this guy. Okay. Now, the one thing I did want to mention, one last thing I wanted to mention, let me restart these routers here so that we can get back to what we were discussing before. Console to this guy, console to this guy. They should recover. If we go back to router 5 and we look at our fault tolerance, there's another reason why we want to make sure that that the secondary routes are feasible successors. Let me do a show IP routing or show IP Eigrp topology one more time. All right, we're still converging here. Router 2 may show IP interface brief. Yep, we've got all of our addresses here, but your router 2 lost a few things. Let's see, Ethernet 1.0 and serial 2.1. Yeah, so the router 2 needs to be reconfigured really quickly. Bear with me a second, guys, here. Interface serial 2.1. That's going to be 172.16.1.2. And interface serial 2.3. And that's going to be 1.5. Should take care of that. All right, let's see if we get our neighbors. We have all of our. Did router 3 crash too? Oh my gosh, router 3 crashed also. So did router 4. All right, hold on one second. Hopefully those don't have to be reconfigured. Show IP Eigrp neighbor. Two neighbors, three neighbors. There we go. Show IP Eigrp topology. All right, now we're back in business here. We should get one more route for 1.0. Actually, we've lost it. That's okay. We've lost it. That's fine. That's not a problem. I know what we set the delay to on that interface. So IP Eigrp topology all dash links. I wanted to do that on purpose anyway because now we're back to our original configuration, which means that we don't have a feasible successor. Now, in the case of Eigrp has the ability to load balance across multiple paths. And we talked about this in our classic configuration way back in lesson number 1 for EIGRP. And what we would do is we would apply a variance command to be able to identify that those paths are considered equal. So clearly the metrics here are significantly different. 229376000 is a lot higher or lower than 30786633958. All right. So if I want to calculate what variance is necessary in order for these paths to be considered equal, I'm going to take the 307, 866, 3958, and I'm going to divide that by the 229376000. All right, so I'm going to need at least a variance of 14 in this particular case in order for those paths to be considered equal. Now, you have to be careful with this because even though EIGRP does do equal cost or unequal cost load balancing, a lot of applications are not really designed for this function because you're going to end up, because we have different paths that have different speeds and bandwidths, you're going to end up with a bunch of, potentially a bunch of segments or frames that are going to arrive out of order. Now that's okay with TCP because TCP has the capability of reordering those datagrams into the appropriate order. But if you're dealing with a lot of different UDP flows, you might actually be introducing a whole bunch of problems in those flows because the data is going to arrive out of order. And a lot of those UDP flows don't have the ability to recover from that even at the application layer. So even though practically it's from an EIGRP perspective, it is something that we can do. You don't always want to revert to this possibility for that very reason. Also, actual load balancing, if you guys remember, is going to be controlled at the switching path anyway, based on a per flow basis from Cisco Express Forwarding's perspective. So even though we might have unequal cost, quote unquote, load balancing, we're not doing equal cost metric-based load balancing. So just some caveats to consider when you're trying to engineer this kind of concept. But let's go into our routing process. Router EIGRP CCIE, address family IPv4, unicast, autonomous system number 1. This is going to be applied to the topology base because, again, it is a configuration that applies to routing and the routing information base for EIGRP. And let's go ahead and set a variance of 15. Now what you would expect is if I do a show IP route, that the 1.0 route is now going to have 3 different paths with to that destination because we have a variance applied of 15. And if I took this metric and I multiplied it times 15, that's the reduced metric, by the way, divided by 128. Multiply that times 15, the other route should fall in between. But the problem is, and this is also another reason that you would want to do this, is that these paths don't qualify, even though the multiplier does, these numbers fit between that value. Because these paths don't qualify as feasible successors, they are also not used in the variance option. So we can't load share across those links based on that variance option. So that being said, we have a bit of a problem that we have to deal with. And that problem is, in this particular case, we have to make sure that those guys qualify as feasible successors. Now, if we look at our topology, what we did is we modified the delay of this interface to 25,000 microseconds, and that fixed that problem rather well for us. So let's go back into router 4, and let's go into interface Ethernet 1.1. Oops, sorry. And let's set the delay to 25,000 again. All right, now let's go see what the impact of that is on router 5. All right. We should see a reconvergence here. All right, and sure enough,
5,000 or 2,500?
Remember, when you enter the delay, it's in tens of microseconds. So you have to multiply.
Okay.
You have to multiply that number times 10. Okay.
Right.
So we now meet the feasibility condition. These other paths, and actually our variance can actually go down now because 15 is not necessary, but we can leave it at 15. So these paths meet the feasibility conditions. So if I do a show IP route Eigrp, I can see now that I'm doing unequal cost load balancing across 3 different paths. Okay. In fact, if I do a show IP route, show IP Eigrp topology 192.168 1.0/24, I can see that these paths are all considered as successors, 3 successors. Now the feasible distance that's being reported here is the best of the 3, but obviously these are not the same, right? And if I do a show IP route, let's see, 192.168.1.0, you can see that the traffic share count between these interfaces is not the same either. The 2 interfaces that have the same metric have a traffic share count of 7, and the traffic share count for the faster interface is 12. That's not exactly like, you know, for every 12 packets on this interface, I send 7 packets on this interface. But it's basically the loading conditions that we're going to apply to those particular interfaces. Keep in mind, again, Cisco Express Forwarding is really going to do the load balancing per flow. So if I do a trace route to 192.168.1.1, make sure I got the right address there. Yep. And I source that from 192.168.0.1. It's going to take a specific path. Let's see what path it takes, based on what Cisco Express Forwarding has defined as the best path. It's taking a long time. Come on, there we go. So it's going to 1.5 and then hitting the router on the left and then hitting the loopback. So in this particular case, it's taking this path here, right? Now, if I was to do that same trace route again, it would essentially take the same path. But if I was to disable Ceph, you would see that it would actually take different paths based on Ceph being disabled. I don't know why it's so slow. Some routers are probably still trying to recover from that BFD experience. All right, so we can see it's taken the same path essentially. So now let's go in here and say config T, no IP Ceph. And we'll do our same trace route. Now we're doing software switching, which means we're now relying on Eigrp to make a routing decision and make a switching decision. So in this case, it would probably might take the same path initially, but it would take a different path each time. So let's see what it takes this time. So now it's going to 2.5. So it decided to take a different path in this case. Now it's going over this link here. And if I was to do the same trace route again, because we're doing this unequal cost load balancing, we should see that it's going to take a different path in this case to that particular destination, based on the fact that I wouldn't say we're necessarily doing round robin, but we're not doing per flow destination load balancing. All right, yeah, it did 2.5 again. All right, I'd have to probably generate enough packets. Here's another way that we can kind of see this real quick. If I do a clear counters, show interface serial 2.3. So we have output rate, input rate. So if I do a ping of 192.168.1.1, source 192.168.0.1, repeat 10,000. Let a few of these pings go out. We should see kind of distribution of these different packets across the different interfaces. Maybe not equally, but somewhat equally across the different interfaces. So let's do a show interface, and let's do pipe out output rate. We won't see it per interface here, but we can kind of infer what the interfaces are. Let me do output rate. There we go. Oh, that's interesting. Why did I not? I probably didn't generate enough traffic because it's a 5-minute output rate. I could do packets output. Let's do that. So you can see it's kind of distributed across the different interfaces, 195, 126, 125. So we're definitely seeing, one of those is a loopback as well, but we're definitely seeing the packets being distributed kind of somewhat evenly. These two are probably the serial interfaces, and this is probably the Ethernet interface. So let's do the ping again. And yeah, so we can see that the load sharing, I don't know if it's exactly kind of a percentage. This is the loopback, so it's getting the hello packets being sent out, but for Eigrp. But you can see that the Ethernet interface is definitely getting more of the distributed packets. So we're not doing per flow load balancing, we're doing per packet load balancing, which could be really detrimental if you've got UDP flows and some of those packets that are going over the serial interfaces are not going to arrive in order when they reach their destination. Now, if I come in here and I do an IPsef again, and I now do the ping, we'll see now that the packets are essentially going to take one interface. Now, which is actually a good thing, right? Because that means the UDP flows are not going to be broken up. And we still get the benefit of, so it looks like it's choosing this interface here predominantly. So let's see if that goes up some more here. Yeah, so that particular flow has been mapped to that interface, which actually is a good thing because on a per flow basis, Ceph is fixing the problem of these UDP flows maybe potentially being broken up, but on a per destination basis or per packet basis, Eigrp is going to try and load balance over different interfaces. So it's not that we can't use the other interfaces. They're still there. They're still part of the route, the available paths for the route, but we're not going to get true load balancing like we typically would see, okay, if Ceph was disabled. All right. So, well, that's about it, guys. Just to summarize what we were talking about here, all right, is this idea of feasibility condition. Very, very important with the Eigrp. Having a successor versus a feasible successor, really, really important. And just being able to manipulate those values and understanding where you need to manipulate those values in order for the appropriate design to be in place for failover, what we call hitless failover. We did mention BFD slightly. I'm going to do a little bit of research and see if there's something else that I need to do with GNS3 to get BFD to work. But I have a feeling that because BFD is a hardware ASIC function, GNS3 is probably kind of freaking out about that. All right, because that normally would have to run in hardware. Tim, I know you have a subscription to Viral, so maybe you can see if it works in Viral. But I would imagine you'd probably run into the same situation with Viral. But all right, any questions? So I'm going to stop the recording.